Okay, so I'm starting the recording here. I want to, we had talked about this example in the last class that I'm going to show you here, but I would like to do it again with you separately from the book and show you why we need these homogeneous coordinates. I think it's a valuable example to look at. So let me give you a moment to copy this example down. Okay, and then we'll go over it. All right. Okay. All right. So in this problem here, we want to find a 3 by 3 matrix that transforms a two-dimensional figure first by shrinking it 30% and then rotating it counterclockwise 90% about the origin, and finally shifting it 1/2 units to the left and 2 units upward. So this is the order in which we're doing these transformations. All right, so how many transformation matrices are needed in this problem, class? How many transformation? That's right, Benjamin. We need to identify 3 transformation matrices, and then we're going to multiply them together to give us the transformation matrix that will do all 3 of these transformations on the object, whatever object we're talking about. In the book, it was the triangle. It was a triangle. So this matrix acts upon coordinates in a two-dimensional XY plane. Okay, so let's go ahead then to the next page here. If we're good, everybody has that copied okay? All right, maybe give me a few thumbs up if you're good. Thank you, Abby. Thank you, Naima. Thank you, Hung. Okay, great, great. So, all right. Well, here's the solution. So first of all, we need to have a matrix that's going to shrink by 70%. And like you did shrinking back in section 1.9. You identified 2x2 matrices that would shrink objects. And this here in the upper left-hand corner is that 2x2 matrix. And of course, what I have above the columns here, above this first column, whoops, hold on. Yeah, above this first column here, I have a 0.3 and a 0. Let me see. One moment. Hold on, class. Let me check this. Yes. Good catch. One moment here. One moment. Yeah, there's an error in what I wrote here, class. This should be shrinking by 70%. So in your notes, please fix that. We are shrinking this object by, thank you, Haley, by 70%. And it was just an error in the writing here. Thank you, Haley. Good catch. All right. Any questions on that? All right. Very well. Well, then, so all right. So for the first transition matrix in the upper left-hand corner, you have your, well, you have the 2x2 transition matrix. And the columns here, this column here is T of E1. This column here, or for that part, is T of E2. So remember, how do you find the transition matrix? Well, you think about. I didn't want to touch that. I'm telling you, man, this eraser's a. We'll get it back. Okay, so that's the transformation of the E1 vector. So the E1 vector, of course, is 1, 0. And if you were to do a scaling of 0.3 or a shrinking of 0.70, 1, 0 would become that coordinate, okay, which corresponds to 1, 0 in the xy plane. If you shrunk that by 70%, that coordinate would become 0.30. And that's how we get the 0.30. Similarly, if you were to take E2, which is 0, 1, okay, and you were in the xy plane, and you were to shrink that point by 70%, it would move that coordinate to the coordinate on the y, so 0, 1 is on the y-axis. So if you shrunk that point by 70%, or scale it by 0.3, that's equivalent, that point would get moved to 0.3. And that's how we get the second part. And of course, the rim here always consists of what you see there, with a 1 in the corner. Now, if you take that 3 by 3 matrix and multiply by the homogeneous coordinate, xy1, then the new coordinate would be, this is your transform coordinate right there. Okay. And remember to get the, hold on here, to get, you know, what's in here, that 2 by 2 portion of the transformation matrix, okay, to get the T of E1, transformation of the E1 vector, and the transformation of the E2 vector, and then, hey, you know, put those vectors together and you have the transition matrix here. That comes from theorem 10 from section 1.9. How many remember that? How many remember that? Doing that. Okay, Benjamin does, and Eleanor does. Okay, great, great. All right, so that's the first transformation. Now the second transformation is to rotate the point, well, or rotate a figure, but rotating a figure is equivalent to rotating the points that make up the figure. The second part is to rotate the figure 90 degrees counterclockwise about the origin. Okay, so, well, okay. In that case, this is the 2 by 2 matrix we would get. And if you rotate, hold on here, you know, if you were to take, hold on, if you were to take 1, 0, that point, and rotate that 90 degrees counterclockwise about the origin, that point would get moved to 0, 1. And that's therefore, yeah, that's that part of the matrix, transformation matrix. And then of course, if you were to take E2, which is 0, 1 on the y-axis, and rotate that 90 degrees counterclockwise, that would get moved to the coordinate -1, 0. Okay, and that's how you get this second part of the transformation matrix. And then, of course, on the rim of that matrix, you have this. Are there any questions on that? So I know that there are formulas, incidentally, for when you have a rotation, there are formulas that you can use to get this, you know, little 2 by 2 matrix, but I find it easier just to apply the theorem, because that's like the theorem 10 from section 1.9 works all the time. So, you know, I don't like to remember a bunch of formulas. If I got something that's, you know, intuitive. And so what I did, well, first, are there any questions? All right, well, what I did then, that's a little bit additional to what the book does, is I say, okay, how would these two transformations, you know, I got the transformation A from where, where I shrink the object 70%, and then the transformation B, where I rotate the object 90 degrees counterclockwise. Okay, rotate the figure, I should say. So do you see that then I do the multiplication here, and my transform coordinate is negative 0.3y, 0.3x. And then you got the little 1 there at the bottom. But is this helping you, the fact that I'm putting in a transform coordinate here, is this kind of helping you see why, like how this is working like how the coordinates are getting transformed? It's just helping you giving you an intuitive feel. Okay, good. Hung likes it, Nafani likes it. Wonderful, wonderful, wonderful. Okay, thank you, Olivia. Okay, so now, finally, the last part is we want a matrix that shifts the figure 1/2 unit to the left and 2 units up. Okay, well, if we do that, okay, that's going to be this matrix here that does that. But now I can't, the changes don't come, I want to say this the right way, the changes needed to produce that are here. Notice like this part here is just the identity matrix of that 3 by 3. But the rim of the matrix, the rim here, okay, is now not going to be what it was for the previous 2 transformations. We have a negative 0.5 here, which corresponds to shifting a 1/2 unit to the left. And then we have a positive 2 here, which corresponds to shifting 2 units up. And then if you multiply C, B, and A, C times B times A, is the order important, by the way, of the multiplication? Is the order important? Absolutely. Absolutely. Okay. If we want, the order of the transformations is important because we're doing the shrinking first, the rotating second. Shrinking comes first, rotating comes second, and then translating comes last. And when you multiply CBA times the homogeneous coordinate xy1, you get this transform coordinate here on the right. You get this transform coordinate. And you see, you need the 3 by 3 matrix so you can move the x coordinate a 1/2 unit to the left and move the y coordinate 2 units up. Okay, you need the 1 here. So that's why we need homogeneous coordinates when we introduce translations as possible transformations for our figures, for our points. All right, let me know, please, if you have any questions. All right, may I move to the next page? Does anybody need a little more time to copy, or are we good? Okay, Abby's good. Okay, Samantha's good. Lewis is good. All right. Okay, well then the final answer, of course, whoops, hold on, I don't want that. Yeah, the final answer, of course, is this is the transition matrix here that will do the job. Okay, that will do the job of these three transformations. And of course, we can program that in a computer, and then it'll make figures do all kinds of things. Okay, well, I mean, this is just one transformation, but if you had a sequence of these 3 by 3 type matrices, you could cause, you could, and you multiply them together, um, based on a little time sequence. I mean, you could have like a game like Pac-Man, you know, I mean, or something like that. There is programming in the chips and so forth that are used. How many like Pac-Man? I mean, I think even though I mean, I grew up with that, when I was a kid, that was like wow, But I think all of you've heard of Pac-Man, and there's Miss Pac-Man too, right? Okay, that's right, Justin. It's not an easy game. Those ghosts will get you. Well, yeah, and they have a baby Pac-Man too, Shravani. I bet you didn't know that, huh? But well, now we've 3 by 3 matrices then will handle two-dimensional transformations. But what if we wanted to work with transforming figures in 3-dimensional space? What size matrix would we need? If we wanted to include translations as possible transformations. For a figure in 3-dimensional space, what size would the transition matrices need to be? Would 3 by 3 be enough? A 3 by 3 matrix? No. Good, Samantha. Good, Hung. We would need a 4 by 4. Okay, 4 by 4. So let's go ahead here and go to another example. Okay, let me give you a moment to copy this example down. Okay, so here, now we're going to consider a figure in three-dimensional space. And we want to find the 4x4 matrix that transforms this figure by rotating it counterclockwise about the y-axis through an angle of 30 degrees. Okay, so we're just looking at one transformation here, one transformation. What would be incredibly helpful to have to start this problem off with? What would really be nice to have? How many think offhand this problem? That's a little difficult. How many are thinking offhand? That's a little bit difficult. Okay. All right. Thank you, Olivia. Thank you, Benjamin. Thank you, Eleanor. All right. Hung has a little kind of a happy, teary face there. What in the chat window? Well, what always helps us to picture things? What might help us to picture things? To picture this problem? A diagram. That's right, Nafani. Very good. So let's go to the solution here and look, solution, right away I have a picture. How do you think I get these lines so straight, class? What tool do I use to get these lines so straight in my three-dimensional picture here? You probably have one of these tools in your drawer at home. A ruler, of course. Okay, so, all right, let me give you a moment to copy this down. See, I guess my thinking is sometimes like drawing a picture like you see here, it might seem a little, maybe a little scary, but if you have a ruler, it's not scary. It really makes your life easier, you know? So, all right, let me give you a moment to copy the figure down. Okay, so again, I think of the theorem 10 from section 1.9 to help me find my transformation matrix. And what I've drawn is I've drawn E1, E2, and E3 here on the diagram. Okay, so of course E1 has coordinates 1, 0, 0. E2 has coordinates 0, 1, 0. That E2 vector, and then the E3 vector, okay, has coordinate 0, 0, and 1. So, okay, so what I'm doing is I'm going to rotate each of these vectors counterclockwise about the y-axis. But which point doesn't get altered by this transformation? Which vector? E1, E2, or E3? Which one will not get changed by this transformation? E2. That's right, Nafani, because E2 is on the y-axis. E2 is on the y-axis. So rotating about the y-axis clockwise or counterclockwise, I should say, 30 degrees. Any point on the y-axis would stay on the y-axis, but naturally the E3 vector up here, okay, that gets rotated 30 degrees counterclockwise. And the E1 vector gets rotated, sorry, the E3 vector gets rotated 30 degrees counterclockwise, and the E1 vector gets rotated 30 degrees counterclockwise. And what I've done here is I've drawn two separate pictures to help you understand the transformation. So in the first one here, I draw the E1 vector, and the transformation of the E1 vector is 30 degrees, being rotated 30 degrees counterclockwise, is right here. Okay, that's the effect of the rotation. So here's E1. It gets transformed to this point right here. And if you construct a right triangle, as I've done here, okay, well, the radius is still 1, and if you think about your 30, 60, 90 degree triangle, in this case, since you're below the XY plane, opposite 30 degrees is going to be -1/2. Okay, normally opposite 30 degrees is 1/2, but since you're below the XY plane, this Z distance here, hold on, should do it. This Z distance here is going to be -1/2. But the I want to say this the right way. But this distance here would have to be √3/2, the horizontal distance, and it would be positive √3/2. So that's why the transformation of E1 is equal to √3/2, 0, -1/2. Transformation of E2 stays 0, 1, 0. And then the transformation of the E3 vector, by drawing another picture, okay, this picture here, you can see it gets transformed to a half 0 root 3 over 2. Okay. Please ask me if you have any questions on the you know the pictures that you see here. Of course, the movement is acting in the XZ plane for those E1, E2 vectors, which is why I labeled the axes as so. I mean, basically, you're looking at this through the y-axis, through the positive y-axis. You're looking at the transformation from that orientation. Now, let me just think on that. I want to be very careful before I say that. Yeah, yeah. I got to be a little bit careful though. Hold on. Yeah, that's right. That's right. I don't know. How many of you maybe look at it from I look at it from the positive y-axis, but I mean, I guess you can look at it also from the negative y-axis, looking this way. But how many find these pictures? Are these pictures helpful for you? Okay, excellent, excellent. Great, great. Very good. All right, well, now that we've identified our transformed vectors, T of E1, T of E2, and T of E3, we're ready to construct our 4x4 matrix. So may I go to the next page? Okay, let me know when you're ready, and I'll move forward. Okay, Abby's ready. Okay. All right. And how about the rest of you, class? You ready to move forward here? Okay, very good. Well, then let's move forward. So this is going to be the 4x4 matrix for the transformation. So see here, we block out a 3x3 matrix, upper left-hand corner. And then these are your three transform vectors. Absolutely amazing. And on the rim, of course, it's just an extension of the 3x3 matrix. And incidentally, what would the, whoops, hold on. What would the homogeneous coordinate consist of? What elements would be in there? Good, that's right, Benjamin. X. Good, Nafani. X, Y, Z, and 1. That's right. Are there any questions at all? Okay, well, I'll just mention there's a numerical note at the end of section 2.7, and it comments that, let me see here, yeah, continuous movement of graphical 3D objects requires intensive computation with 4x4 matrices, particularly when the surfaces are rendered to appear realistic with texture and appropriate lighting. High-end computer graphic boards have 4x4 matrix operations and graphics algorithms embedded in their microchips and circuitry. Such boards can perform the billions of matrix multiplications per second needed for realistic color animation in 3D gaming programs. Okay, this is a comment at the end of section 2.7 in your book, numerical note. How many think that's absolutely fascinating? I mean, what you're learning here is used in computer games. Yeah, it's really cool. I agree, Lewis. Crazy and cool, right? All right, what I'd like to do, I'd like to give you about 15 minutes here to work on the section 2 point exercises. So on, like your homework for Wednesday will cover section 2.7 and at least some of 3.1. But let me give you a little time to work on section 2.7. So let me make that available right now, and I'll stop the recording here if we're good.